So you were describing from roughly 2010 to 2020, if I'm remembering correctly, that was kind of like your research phase. And in that phase, you were prolific. So one main focus of your research has been interpreting and understanding deep learning models. We already talked about the Deep Viz toolbox. So, being able to visualize intermediate layers in the many layers of a deep neural network, which is what makes it deep. For people who aren't already familiar with the way that deep learning works, that you have layers of these things called artificial neurons, which are very loosely based on the way that biological neurons, biological brain cells work in your own brain, in a human brain or an animal brain. And yeah, by layering these together, there's a lot of capabilities. So when you are having a conversation with your ChatGPT or your Claude or your Gemini, that incredible amount of nuance and understanding comes from just layers of these artificial neurons being able to do increasing complexity, increasing abstraction as you go deeper. But simultaneously, that all of those layers, all of those neurons make it difficult to interpret what's going on inside of a model. So tools like your DeepViz toolbox allow you to see, and people should really check out this YouTube video. It's amazing. It allows you to see not just layer by layer what's going on, but neuron by neuron. And so, for example, my favorite part in the video is when you are on camera and you are highlighting a specific neuron it's in convolutional layer 5 of the network. There's 256 artificial neurons in that layer, and one of those neurons, based on the particular training data that this machine vision model was trained on, so it had to the machine vision model had to become capable in a broad range of different kinds of images. So some of the neurons became specialized in detecting text. Some became specialized in detecting dog faces. And one of them, in particular, became specialized in seeing human faces. And so in real time in this video, you're on camera, and as you move your head to the left, to the right, you can see this white hot activations happening for that specific neuron on the pixels that your face is in. And to make it even more compelling, there's a point where you bring a colleague in to the video and he joins you in the frame. And then we have these two white hot areas of pixels representing where the faces are in the video. So really cool tools for being able to allow us to understand what's going on. And I think convolutional neural networks.
I think it's funny that we just had a 1 minute explanation of that, but like if we could actually just show it, it would be more obvious in 10 seconds or something, which is maybe
for sure
toolbox in the first place.
Absolutely, and that's the there's all kinds of things we would love to show people, but because almost 90% or more, 95% or more of our listeners in a typical episode are audio only, so yeah. Although you and I,
describing the white hot activations is as good as we're going to get.
Yeah, exactly. So yeah, so my point is getting all this with convolutional neural networks, with machine vision problems. Those are cool because visualizations are kind of there's something that kind of comes quite naturally from that. Whereas today, some of the most impressive generative models, certainly the most widely used generative models, are outputting text. And so that becomes harder to visualize in a cool way like you did. Anyway, as models continue to get bigger and bigger and bigger, that's a whole other dimension here. So as they become, as we're talking about models that aren't visual, and as they get bigger and bigger and bigger, how can we continue to understand what's going on in them? Or does that matter at all?
Yeah, no, great questions, and questions that I don't really have the answers to, and a lot of people maybe don't necessarily have the answers to. A lot of topics. So as models get bigger, they certainly get more complicated. They certainly get harder to understand. Even back in I think it was 15, when we published the DeepViz toolbox, that model had 60 million parameters. And like you mentioned, on one of the layers, Conv5 had 256 neurons. Even that model, even I, who wrote the paper, played with the toolbox maybe as much as anyone, scrolling around to all the different neurons. Even I can't claim I understand what was going on inside, right? We found a face detector. That was great. But it just happened to fire a lot for faces. We didn't actually know whether it would fire 0.6 and not 0.5 for another part of an image that was not really face-like, but a little face-like.
Yeah,
Nor
or
did
like
we know that
a
that point 0.6 versus
monkey,
point 0.5 was very important. Like,
a
maybe that
monkey
was critical.
face, or a
Yeah.
dog face, or a clock face.
Yeah, for sure, for sure. It would fire for monkey faces and dog faces. Um, but we just by seeing it fire doesn't mean you understand everything it's doing in all the downstream layers. And actually, the layer right after Conda 5 was in this network FC6, so the sixth layer, fully connected layer. It had 4,000 neurons, 4096, right? So you see these 4,000 little things spiking. You could try to scroll through every single one, but like, what would it take for you to claim you understand what's happening? We're probably not going to get there. Nevertheless, showing the Deep Viz toolbox, I think, teaches people who don't know how networks work a lot about how they work very quickly, which is, I think, uh, something I was proud of in that paper. Also, if you work with convolutional networks, it teaches you like subtleties of how these networks work that might not have been obvious before. As a practitioner, as someone trying to debug a network that might be broken or not training well or not generalizing well, just seeing high bandwidth visualizations, I think, can often help. So I think that fact, let's now fast forward a couple of years to get to where we are today with like much, much larger models. I think that fact still holds. So seeing visualizations for how networks are working is probably still useful to people trying to debug problems with those networks, but it has not led to, and probably will not lead to, full human understanding of what's going on inside. So I think it's like useful as a tool in a practitioner's tool belt, but will not make models on their own explainable.
Nice, makes sense. And so, do you think that that experience, and I realize that now as we get to models, large language models behind things like GPT-4 might have, and we don't know because haven't officially published it, but there might be a couple billion artificial neurons in there. There's no chance of us kind of, in the way that you were able to go over the 4,000 neurons or the 256 neurons in an architecture like it was Linnet 5, I think, that you
Uh,
went
it
through
was
there,
it was AlexNet or a
or AlexNet. Yeah, yeah,
derivative
yeah.
of AlexNet. Yeah.
AlexNet, yeah. And so, of course, what was I thinking? It's way too many convolutional layers for the net. Anyway,
Yeah.
um, yeah. So as you're saying, it becomes, even there where you're looking at hundreds or thousands of neurons in a layer, millions of neurons total, it is difficult to interpret too much, but you can still get some sense of what's going on, maybe learn a bit, understand where things are working well, things aren't working well.
Mm. Yeah, just having the basic, like, starter visibility into something about the network was at the time really important and is still important. So when I started working on this, I was at, it doesn't matter where I was, somewhere working for the summer, and I was working on kind of like my real project, which had some, possibility of publishing like a normal paper. And I realized like nobody had made plots of what's happening inside of the network, just like a live video plot of what's happening as you feed in some video stream. And so this became just like a weekend project. Like I just wanted to see it for myself. And as I worked on it, I realized I was really frustrated with just like how little we know about what's actually happening in the network. Like as you train a network, what do? You watch the loss. It starts out really high and like it shrinks over time, you hope. And that's the training loss. And maybe you watch the validation loss too, and you see that shrinking a little bit too, but maybe not quite as much. But that's like you're watching a scalar, and there's like so much magic or maybe broken parts happening inside of a network training, and you can only see this like one little number decreasing. So, for example, let's say I went into your network, you initialized it, I went into your network, and I just randomly set half of one of the layers to zeros, and I left the other half okay, the same. If you start training, it'll probably still train. The loss will go down. It might be like really subtly broken in some tiny way. But like you as a network trainer have no basic visibility into the fact that I just like broke half of one of your layers because there's like no visualization you even watch as a matter of regular course to see this. Or let's say I go in and multiply one layer by 10 and divide the next layer by 10. The net Jacobian or whatever beginning to end is the same, but the training process will proceed very differently. Would you be able to detect that by looking at your whatever plots you normally look at? Probably not. So it was funny. This was true in 2015. And so we started working on a couple of these papers to try to produce greater visibility. But I think it's still true today. Like I think most people that train networks, they click go, either it works or it doesn't. And if it doesn't, they try something else. Why don't we have like the oscilloscope for training? Why don't we have the oscilloscope for network operation representation and so on?